Page 84, we're going to start into topic 2. First lesson is going to be on ratios, rates, and unit rates. Before we get into that, if we look on 84, we're just going to look at a couple things here. So if we look at the vocabulary, choose the best term from the box to complete each definition. So number 1, the quantities x and y in the ratio x over y are called. So that would be terms. Number 2, 2 dogs over 3 cats and 10 dogs over 15 cats are an example of, and that would be equivalent ratios. Number 3, a or and blank is a type of ratio that has both terms expressed in different units. And that would be a rate. And number 4, a or and blank has a fraction in its numerator, denominator, or both. That would be a complex fraction. Okay, so that's a little bit of vocabulary for you to start out here. Not to spend too much with this, but we could just look at on number 5. They want us to complete these equivalent ratios. What we can do for these sometimes is find a pattern. So 4 boys for every 7 girls, that would be 8 boys for how many girls? We can just look and see how do we get from 4 boys to 8 boys. We're looking for an answer of multiplying by something or dividing by something to get there. So that would be 2 times as many boys. So if we keep the same ratio, that would be 2 times as many girls. 7 times 2, so that'd be 14 girls. And then this next section, it says write each situation as a rate. I'm going to be more specific and say let's write these as a unit rate. And again, some of these will be things we'll be looking at in this lesson, but we've also looked at them before as well. Unit rate basically has a denominator of 1. So 150 miles in 3 hours, I could put it as 150 miles over 3 hours. That's for 3 hours. If we can figure out for 1 hour, that's called a unit rate. And basically, to figure that out, we can actually just divide these numbers out, and that will give us our unit rate. If you want to think about, I'd have to divide by 3 to get that to be a 1. That's fine. Would be 50. So that's 50 miles per 1 hour, which you could also then just say is 50 miles per hour, like that. We have another abbreviation since it's just so much work to write miles per hour. You might see it as MPH for miles per hour. Most other countries are going to probably not be too familiar with that, I wouldn't think, because in their countries they are going to see an M as being meters. That's why we normally do MI for miles instead of just an M. But anyway, it's just such a common abbreviation, MPH for miles per hour. And then if we look at number 13, they want an equation that represents the pattern in the table. Usually when we write these equations, we're going to try to write y equals something. So what we can try to do, if it's an easy pattern, we can try to look for how we get from our x values to our y values. So how do we get from 4 to 12, 5 to 15, 6 to 18, and so on. So it's multiplying by 3 for each one of these. So what that means is our y values are equal to 3 times what our x values are. So we can write our equation as y equals 3x. If you want to put parentheses around the x or something, you can, but just remember if the x is after the number, it's assumed that we're multiplying those together. So we look on page 85, starts out our lesson here. In this lesson, what we're going to be doing, just to make things a little quicker for you, we're going to show our work. If we show our work, then you can use calculators just to make the calculations a little quicker for you. So on 85, in a basketball contest, Elizabeth made 9 out of 25 free throw attempts. Alex made 8 out of 20 free throw attempts. Janie said Elizabeth has a better free throw record because she made more free throws than Alex. Okay, so yeah, she did make more. She also shot more, so we'll have to see how that looks. So what we can do, Elizabeth made 9 out of 25, Alex made 8 out of 20. So one thing we could do is just divide these out. So like 9 divided by 25, you could do that. Another option would be we could try and get a common denominator and say, well, 25 and 20 aren't the same, but let's get them to having the same number that they shot. So if we did a common denominator, 100 would be the smallest denominator that would work. So that would be 36 out of 100. Okay, this is Elizabeth. Would, on average, we would think maybe make 36 out of 100. And then Alex would multiply those by 5. We would expect to maybe make 40 out of 100. So 40 out of 100, that's more than 36 out of 100. So actually Alex has a better free throw percentage is what we would call it usually. The other option besides getting a common denominator is you could actually just divide these out. So if you just take 9 divided by 25, you get 36 hundredths. If you take 8 divided by 20, you get 4 tenths. What those are basically, if you move your decimal over 2 spots, that's their free throw percentage. So Elizabeth has a 36% free throw percentage, and Alex has a 40% that he made. Okay. As people go along, if you watch sports and stuff, I mean, a lot of times if in college and stuff, people will be maybe good free throw shooters, maybe 70 or 80%. Nobody's guarding them, so they can be a little bit better at shooting those maybe than some other shots. So a few definitions we're going to talk about here before we get going. First of all, a ratio we can say is a comparison of two things by division. So example, 2 over 3. Okay, maybe 2 pens for 3 pencils or something like that. We can also write it with a colon in between there. That means 2 to 3. So that's a ratio. Another thing we've got is a rate. So rate is a ratio with 2 different types of units. So for example, 200 feet over 5 seconds. Feet is a distance, seconds is a time. Distance and time, those are different types of things. $78.75 for 9 hours. Dollars and hours, different types of things. I'm not going to convert, I can't convert dollars to hours or hours to dollars. Doesn't make sense. So those are called rates. More commonly, we're going to be more interested, instead of rates, we're going to be more interested at finding unit rates. So unit rates are ratios with a denominator of 1. Ratios with a denominator of 1 are called unit rates. So for example, let's take our rates we just talked about. So we had 200 feet for 5 seconds. If I divide that out, I'll get a unit rate. If I do 200 divided by 5, that will give me 40 feet per second. 40 feet per 1 second. If you want to write it as a denominator of 1, or you can just put 40 feet per second. Also, $78.75 for 9 hours. If you divided that out, 78.75 divided by 9, then that should be $8.75 per hour. Again, that's per 1 hour, or you can just write $8.75 per hour. That line, that slash line means per. So if we look at example 1, Nathan and Dan were both hired as lifeguards for the summer. They received their paychecks for the first week. Who earns more per hour? So we can see what they've got here, what their earnings are. What we can do basically is finding our unit rates here. So for the one of them, for Nathan, it was $46.25 for 5 hours. You can divide those by 5. If you'll notice, what we're doing here is the same as just dividing these numbers. So if you want to just take $46.25 divided by 5, and that's $9.25 per hour. And then for Dan is $78.75 for 9 hours. If you divide that out, you get $8.75 per hour. That's where I got my example a minute ago, you might have noticed. And then the question is, who earns more per hour? So we could say by that, $9.25 is more than $8.75, so we could say Nathan earns more per hour. Specifically, if we want to be more specific, we could subtract these. If you subtract these, you'll get 50 cents. And then we could say that Nathan earns 50 cents more per hour. So if we look at the try it, Jennifer is a lifeguard at the same pool. She earns $137.25 for 15 hours of lifeguarding. How much does Jennifer earn per hour? So we can see from this was $137.25 for 15 hours. We're trying to figure out for 1 hour. So we need to get that unit rate. And just to make this quicker process for you, if you're showing your work of what you're doing, you can use a calculator to work these out. So if you want, we can come over here, look at this proportion, 137.25 for 15 hours. To go from 15 to 1, we have to divide by 15. So to get something equivalent to that, we also have to divide our money by 15. And if you divide that out, you get $9.15. So $9.15 per hour. Some of this you might think it's an odd thing that these people are making different amounts of money and they're got the same job, but a lot of times it has to do with experience. If you've been there longer, then you can make more money, because I guess they're assuming if you've done it longer, then you can maybe do a better job potentially. Or it's just kind of how you got to work your way up the ladder, so to speak. So example 2, Brian agrees to watch his neighbor's dogs for 7 days. His neighbor provided a 128-ounce bag of dog food. Does Brian have enough food to feed the dogs all 7 days? So if we look at the information here, Buster eats 20.5 ounces in 2 days. Roxy eats 22.5 ounces in 3 days. You know, of course, they're not going to tell us just how much they eat per day because that'd be too easy. So what we could do is what the book did. They said, okay, that's for 2 days. Let's see how much Buster eats in 1 day. So they divided by 2. They got 10.25 ounces for 1 day. And then they said for 7 days, it'd be 7 times that amount. So 71.75 ounces. For Roxy, they did the same thing. Divide by 3. So that's 7.5 ounces per day. 7 days would be 7 times that amount, would be 52.5 ounces. And then once they got those, they added those two together and they got 124.25. They've got 128 ounces, so technically then they do have enough, just a little bit left over. Okay. Another thing we could have done is found the amount needed per day for each dog and added those together and then multiplied by 7. Not a big difference, but just one less step. So like we found out, Buster is 10.25 ounces and Roxy is 7.5 ounces. We could have added the 10.25 and the 7.5 and just said overall I need 17.75 ounces total for the day. And then we could take that and multiply that by 7 and we should get that same answer, the 142.25. So if we look at example 3, suppose each jump covers the same distance. How many jumps does it take each animal to cover the same distance? So in other words, the rabbit, each jump is 8 meters. The the rabbit altogether jumped 8 meters, but each jump was the same distance. The kangaroo rat altogether jumped 12 meters. Each jump was the same distance. So one option we have, if we look at the rabbit, we could figure out some equivalent ratios until we get something that's the same. So if 3 jumps for the rabbit took them 8 meters, if we just double those, 6 jumps would be 16 meters. If we go back to the original numbers, 3 times that amount, 9 jumps would be 24 meters. And then we can do the same idea with the kangaroo rat. So if we double both of those, 5 jumps for 12 meters, we double both of those, 10 jumps was 24 meters. If you'll notice, we have a winner here. Both of these are 24 meters. We've got a same distance, but if you'll notice, the rabbit took 9 jumps, the kangaroo rat took 10 jumps. So we can see that the rabbit is going to jumping a little bit more per jump, and that would be also where we could say, to get the same distance, the rabbit could jump 9 times and the kangaroo rat could jump 10 times. And this is kind of like getting a common denominator when we're doing this, because it's kind of like we had 3 jumps for 8 meters and 5 jumps for 12 meters. So we could put units next to those if we wanted to. And then just say, well, I've got 8 and I've got 12. How can I get those to the same? Just like we do for getting common denominator for a fraction. So we could say, oh, 24 works. Now that would be 9 jumps for 24 meters. And then this we need to double those. So that would be 10 jumps for 24 meters. Okay, so just a different way of looking at it rather than doing a table. If you want to just do fractions like that, that's fine also. So if we look at the try it, a kitchen sink faucet streams 0.5 of a gallon of water in 10 seconds. So half a gallon in 10 seconds. Bathroom sink faucet, that's the kitchen sink faucet. Bathroom sink faucet streams 0.75 of a gallon of water in 18 seconds. So the question is, which faucet will fill a 3-gallon container faster? If you think about this, it actually, the size of a container that we're filling really has nothing to do with this problem. Whether it's a 3-gallon container, a 5-gallon container, whatever it is, it really has to do with which one has the faster rate of dispensing the water. So one way we could do this then is actually just to do these as kind of unit rates. It's 0.5 gallons in 10 seconds. So if we divide those by 10, that'll tell me how many gallons per second. That's just going to move our decimal over one spot. So that's 0.05 of a gallon for 1 second for the kitchen sink faucet, and for the bathroom sink faucet, if we divide both of those by 18, we're going to get like 0.0416 repeating. The 6 is repeating only there. Gallons per second. And then we can just compare these. Well, they both have 0.10. This one has 0.05. The other one only has 0.04. So this one, the kitchen sink faucet, must be the faster one. Okay. And again, technically, if we wanted to figure this out for 3 gallons, we could do that. Half gallon in 10 seconds. To get to 3 gallons, that would be 6 times as much. So that'd be 60 seconds. And the other one, 0.75 to get to 3. 2 of those would be 1.5, so we need 4 of those to get to 3. And then that would take 72 seconds. So specifically, even we could say, you know, the kitchen sink faucet would fill it up 12 seconds faster, of which by the time we worked this out, I'm sure that 12 seconds would be lost. But anyway, we could figure it out. If we were doing a lot of buckets, then that might be important information to know.